Hi, okay, so today's topic is sub-exponential. Before today's lecture, let's talk about some notes. So why I made this series of videos? There are basically four reasons. The first reason, of course, is to practice English speaking. Of course, I can use Chinese Mandarin to give these lectures, but as you know, I'm gonna to take part in some graduate program in the United States, so I'm trying to practice English speaking. And the second reason is about self-study. So I think it's a highly self-motivated process of me to do this reading work. So I know it's very hard to focus on reading such a difficult book, but it's very important. So I try to use this method to motivate myself to be focused on this book. And the third reason is that I know that someone else would also have the chance to face with the same questions later, and they may, try to find out if there are some resources available on the internet. So I made this clip of videos. So if someone else want to find some tips on some specific problems, they may find it helpful by watching my videos. So the fourth reason is about the record of study. If I do not make these clips of videos, I may, instead I would like sleep or play computer games. So it's a way to record my study, also a way to let me focus. So this is the reason why I would like to make this series of videos. So anyway, today's topic is about sub-exponential. In lecture 2, we talked about sub-Gaussian and Chernoff bound. So today, we talk about sub-exponential. As you know, we wanna, consider some relaxations on sub-Gaussianality assumption. So this is where the sub-exponential variables comes from. And this is defined by a slighter milder condition on the MGF, moment generating function. So the definition looks like this. We name a random variable with finite mean a sub-exponential variable if there exists non-negative parameters mu and alpha such that this is satisfied. So we could compare this condition with that of sub-Gaussian here. Let me see. So if the random variable is sub-Gaussian, it says that for any lambda belongs to the real set R, this inequality should be satisfied. But for this sub-exponential, we do not, lambda is not required to satisfy this inequality for all R, but we give it a non-negative parameter alpha such that when the absolute value of lambda is less than 1 over alpha, this is satisfied, then we call the random variable x a sub-exponential variable. Of course, sub-Gaussian is sub-exponential by, choose mu equals to sigma and alpha equals to 0. And we interpret 1 over 0 as being the infinity, then sub-Gaussian is also sub-exponential. But the converse statement is not true, that if the variable is sub-exponential, we should not conclude that it's also a sub-Gaussian. Here's an example, like this chi-squared random variable, but with degree of freedom equals to 1. So this is the standard normal distribution. There is such a random variable, and we let x equals to z squared. Then when lambda is less than 1 over 2, we can calculate the MGF like this. So we know that when lambda is larger than 1 over 2, this is when lambda is less than 1 over 2. Like here, we can use this inequality to derive that this x is sub-exponential together with the parameter mu and alpha equals to 2, 4. But when lambda is larger than 1 over 2, you know that the MGF here is infinite. So x is not sub-Gaussian. But we can derive that this is sub-exponential. And proposition 2.9 tells you the tail bound of sub-exponential. So we can compare this tail bound with that of sub-Gaussian here. The sub-Gaussian looks like here. The coefficient of the power over E is equal to negative t squared over 2 sigma squared. And here is something like, it's like an if-else condition. When t is less than something, it looks like the behavior of that of sub-Gaussian. But when t is larger than mu squared over alpha, the exponential term is linear of that of t. So this is the difference. When t is less than mu squared over alpha, is the behavior of sub-exponential looks like sub-Gaussian. But when t is larger than this cutoff value, it behaves linear over the exponential term of e. So the proof is by using the Chernoff bound here. So we wanna calculate the minimum value of g lambda t over lambda, where lambda belongs to this range. So let me see why lambda belongs to this range. Okay, by definition of sub-Gaussian. So when t belongs to different intervals, we get the different optimal value of the function g. So this is why we get this if else different conditions of this tail bound. Okay, now since we will talk about the Bernstein's condition, which is the equal condition of for that x to be in a sub-exponential random variable. Let me see. So here we could control the polynomial moments of x so as to get the property that x is sub-exponential. So let me see. Yeah, to the sub-exponential property can be verified by bounding the moment generating function, and an alternative approach is to control the polynomial moments. So we derive the Bernstein's condition like this. And since we know that if x is bounded, x is sub-Gaussian, and we get the sub-Gaussian type bound like, what's the sub-Gaussian type bound? Is Hofstee bound, right? So now when x is bounded, x is also sub-exponential, and we can also get the Bernstein type bound. Looks like this. So when x is bounded, this equation holds, and of course it satisfies. We can verify that this condition holds. And let me see. But this condition holds for more circumstances than these bounded variables. So here it says that Bernstein's condition also satisfies by various unbounded variables, and is much broader applicability than that of bounded variables. So when x satisfies the Bernstein condition, then it's sub-exponential. By calculating this power series expansion of exponential, we can easily prove this. Here we use the Bernstein condition, and in this range of the absolute value of lambda, we can calculate the geometric series to obtain the final results and conclude that x is sub-exponential with these parameters. And here is the Bernstein type bound. For any random variable satisfying the Bernstein condition, we have this bound, and the concentration inequality looks like this. So it seems that this is different from the direct property of sub-exponential here. So this is the sub-exponential tail bound, but here, when it satisfies the Bernstein condition, which also means that it's sub-exponential, we have another bound named Bernstein type bound here. So it looks different than that of the sub-exponential tail bound here. We can make the comparison. So this calculation of MGF is less than this. Here, the denominator looks like 1 minus b times the absolute value of lambda, but here, in the definition of the sub-exponential, there's no such term, and we get the concentration inequality. This is from the definition of Bernstein condition. So when the random variable satisfies the Bernstein condition, we know that it's sub-exponential. But what if the variable is sub-exponential but not satisfies the Bernstein condition? Let me see the definition of sub-exponential. It says that this is satisfied. I think you can figure out an example that is sub-exponential but not satisfies these Bernstein conditions, because this type of bound seems more tight than that of sub-exponential. So this proof is intuitive. By setting lambda equals to this value in the Chernoff bound, we get this bound. And I'll calculate this, and I have to mention that this calculation is not optimal. Let me see. Here. I've calculated this Bernstein type bound, and it seems that the choice of lambda is feasible because it belongs to this interval, but it's not optimal turnoff. Anyway, we get this type of bound, and we can use this bound to do further calculation and derivation. And here's the remark. This proposition shows that for bounded random variables, we have different ways to deal with these bounded random variables to get the different types of its tail bound. For example, when it's sub-Gaussian, we can get a bound, and we can apply this by applying the Hofstadter type inequality. And since that's bounded variable, bounded variable satisfies the Bernstein condition, And we can apply this Bernstein type bound, which involves both the variance and the bound B. So there's a time that when sigma square is substantially less than b square, where b is the bound of the random variable. As would be the case that a random variable occasionally takes on large values but has relatively small variance, then it seems that sub-exponential bound seems better than that of Gaussian because we incorporate the value of sigma here, but not b. Let me see. So sigma square is much less than that of b square. And let's say the bound when t is small, then this term equals to 0, and since sigma square is less than b square, then applying this sub-exponential tail bound, this Bernstein type bound, is much better. So we get the somewhat sharper control on the tails. So this is the example when you are trying to use the Bernstein bound or that of Hofstee bound. Here's the choice between these two bounds. And like the sub-Gaussian properties, sub-exponential also satisfies the preservation under summation. The proof is also intuitive by some arithmetic calculation, algebra calculation. And finally, there are two examples of sub-exponential. The first one is chi-square variables, and the second example is the direct application of chi-squared variables. So this is called Johnson-Linden-Strauss embedding. So we assume that we have n larger than 2 distinct vectors. This is typically with high dimension, and we want to contract the mapping so that the dimension with the mapping of f is substantially smaller than the original dimension d, and we also want to preserve pairwise distance under the norm and inner products, which means that the distance after the mapping and before the mapping, it has some tolerance delta, and it looks like, and we have this formula. Here's the way of construction. This construction is probabilistic. We set the random matrix X with every entry like this independent standard normal distribution, and we define a linear mapping like this. Then we can verify that f is satisfied. So here, this inner product follows the standard normal distribution. You can verify this by calculating this inner product. Then if some some form of some combination of different say standard normal distribution, and the combination, if you calculate, then it satisfies the standard normal distribution. So this also follows the standard normal distribution, and we get y, which is exactly the mapping of we can transfer this into the mapping f, and we get y that follows the chi-square distribution, and we get the tail bound. And rearranging the definition and recalling the definition of f, we finally get what I want. So this is the bound of this this mapping we construct. since there are different, say, choose 2 from n distinct pairs of data points, we apply the union bound, so we get the final result here. This is the bound we want. So for any epsilon belongs to this range, the probability can be driven below by some calculation. So we choose m must be larger than this. This, interestingly, is actually independent of d, where d is the original dimension of our data sets. So this m, the dimension we want to choose, is independent of that of d and only log with the data points n here. So this is an interesting property. So it seems as if we have too much points, or we set different epsilon and different delta, different tolerance delta, then we may not achieve our goal to embed a higher dimension to a smaller dimension. So this is an interesting property. So this is example 2.12. Finally, it also gives some equivalent characterizations of sub-exponential variables. We can have a brief review of that of sub-Gaussian here. Sub-Gaussian, the first one is a definition. The second one is by dominance of the Gaussian random variable. The third one is the constraints of the moment, especially the even order moments. The fourth condition is something, here the power is x squared but not x. So this is about sub-Gaussian. So when we are talking about the equivalent characterizations of sub-exponential variables here, there are also 4 equivalent conditions. The first one is definition. The second one is saying that if there exists a positive number, so that the expectation of exponential lambda x is finite. So this is an interesting characterizations of sub-exponential. And the third condition is to make sure that x, this probability, is bounded by some exponential-like function. So I guess this is why it's called sub-exponential, because it's dominant. It's bounded by an exponential-like function. And the fourth one is by calculating the supreme of this. So this is to guarantee that the power series is finite. So we will talk about this later. The first proof is from 2 to 1 by using the Taylor expansion, and from 1 to 2 is trivial. From 3 to 1, now if it's bounded by some exponential function, here we set a truncation level. So here the author used 2 tricks, and I write it here. Let me see. Section 2.5, appendix B. Let me see. I remember I made some notes here. So there are several tricks the author used to prove the desired results. So first of all, the author sets a truncation level t. So first of all, why we need this truncation? The author sets t larger than 0, and this, I don't know why he used this inequality. I guess this is equal. So this equals to this by regard this term, the exponential with the power ax absolute value of x regarded as a whole, then this is non-negative, so we get this calculation. Then we telebar this integral from 0 to 1 and from 1 to e a t. So the integral from 0 to 1 is less than 1 because the probability is must be no larger than 1. And here is an equivalent transformation from this to this. So applying the tail bound, we obtain the final result here. So this comes from that you make this a to this range, you transfer a to c2 over 2, and you get this final result. So we have this, let me see. This is based on direct calculation, and this inequality comes from, you let this a to the upper value of c2 over 2, you get this. And finally, by taking the limit as t tends to infinity, we get that the expectation is finite. Finally, we get the result we desire. So by proving 3 to 2, the author used 3 tricks. The first one is truncation level t, and finally take the limit as t tends to infinity. And the second trick is by telebar the integral from 0 to 1 and from 1 to another value. The third trick is about the inequality. Use the inequality to make a larger to that of c2 over 2. So we get the final results. And from 2 to 3 is by applying the Chernoff bound with the given value of lambda. And the equivalence of 2 and 4 is by the definition of radius of convergence of power series. So this is also called the Cauchy-Hadamard formula. Cauchy-Hadamard formula. It gives you the definition of the radius of convergence of this power series. So the equivalence of 2 and 4 says that if the expectation of this exponential term is finite, then this quantity must be finite, because we can write to here. The MGF looks like this. So to make sure this is finite, this series converges. So we have to make sure that the radius of the convergence of the power series. So I have to make sure that the radius is finite here. So by the definition of the radius of convergence of power series by the Cauchy-Hadamard formula, we get this, which is also the statement 4 says. So this quantity gamma is finite, means that the Taylor expansion of this is satisfied. So this proof is intuitive. I write it here. So by the definition of supreme, or the upper limits, we get the final result. So here it says we can choose any little alpha larger than big alpha. Then by the definition of the supreme, we get that this does not approach 0 for any z with this larger than r. So the power series diverges. Let me see. Because this is larger than 1 for infinitely many indices, then this summation does not converge, of course. And also when little alpha is less than big alpha, then we get the series. The summation of these terms must be finite, so we get that the radius of the convergence is r. Finally, there are some one-sided results. We know that the absolute value of x is bounded, but x has some upper bound, and we get this proposition 2.14, the one-sided Bernstein inequality, like this. And also, if we have n independent random variables, we satisfy the the upper bound. It has the upper bound, then we get these results. Also, if we have a non-positive or a non-negative random variable, we can also apply the Bernstein bound and get these results. So here it says that the lower tail of any non-negative random variable here satisfies the bound of this is sub-Gaussian type, of course, but albeit with the second moment instead of the variance. Here we write the second moment, but in the sub-Gaussian type, here is the sigma square, it's the variance. Here is the second moment for this non-negative random variable. So the proof, well, let me see if I want to talk this proof into details. So the author wants to calculate this, and apply the Chernoff bound. Let me see. So to prove 2.22a, to calculate this term, they also want to incorporate let me see. So there is the inequality to write since x less than b, we have this, and hence this is less than this. This expansion is equal by using the definition of function h, and by calculating this, we transfer this lambda x to lambda b, and hx is increasing in r. This is an increasing function, by the way. So let me see. From this to this, here is also an assumption that x is 0 mean. Let me see. Not 0 mean. So why it gets from here to here? Oh, alright. This comes from another inequality, I guess. 1 plus x is less than ex, right? Yeah, it's another inequality applied here. 1 plus this is no larger than e with the power lambda ex plus this. So by summation, we get these results. Then we show this. H lambda b here is right. The power series, and also by some inequality, and get final results. Well, anyway, there are some tricks by calculating this. And to prove the part B, the author also applied the Chernoff bound. So anyways, this incorporates some tricks, so I don't want to talk into details. Anyway, this is what we have learned today. It's about the sub-exponential bounds, sub-exponential variables and Bernstein type bounds. So we compare this with that of sub-Gaussian, and it has a slightly, milder condition on the moment generating function. And under different circumstances, we may apply different bounds, Hofstee bound or Bernstein bound. If you have the information of variance, and when t is smaller or larger, you may apply different bound based on the formula of different bound. So this is the end of section 2.1. We talked about the Chernoff bound, the sub-Gaussian variables, sub-exponential variables, with summary with several equivalent conditions of these variables and some properties of these variables. We have two-sided results of and two-sided bounds and also one-sided results. So this is the end of lecture 3. Thank you. Goodbye.